Welcome, this is Prajwal GH. Today we'll explore advanced materials for next generation solar cells, how they work, and what's new in 2025 and where they are being used. Why next gen solar? Solar power is clean and abundant, but conventional silicon cells are close to their efficiency limits. That's where advanced materials come in, promising higher efficiency, flexibility, and new applications. Basic principle of a solar cell. Solar cells works on the photovoltaic effect. Light excites electrons in a semiconductor, generating electron-hole pairs. These are separated by an electric field at the p-n junction, creating current and power. Let's watch how solar cells works.
Commonly used renewable energy source is solar energy. But how is solar energy used to generate electricity? A photovoltaic or PV system is used to convert the solar or light energy into electrical energy. The basic component of the PV system is known as the solar cell. A single solar cell has the capacity of producing about 0.5 volts of electricity. A solar panel or solar module is the combination of several solar cells connected in series to generate usable voltage. The solar panel voltage can be increased by increasing the number of solar cells. For example, 30 solar cells connected in series will produce an output of 15 volts. A combination of solar panels connected together is known as solar array and can be used to achieve required current and voltage. How does the solar cell work? The generation of electricity on exposure to sunlight is known as the photovoltaic effect. This principle is used by solar cells to produce electricity. The solar cells are made up of semiconductors, mainly silicon, and comprises three layers. The top layer, called the N-type layer, is comparatively thin and contains high concentration of electrons. The bottom layer, called the P-type layer, contains high concentration of holes. When the P-type and the N-type semiconductor is joined, it forms a p-n junction. On forming a p-n junction, the electrons of the N-type material try to reach the p region, creating a negatively charged layer. Similarly, the holes of the p-type material try to reach the N region, creating a positively charged layer. This region between the two layers is known as the depletion region of the semiconductor. Sunlight penetrates the top thin layer easily to reach the depletion region. Due to the deficiency of charge in the depletion region, it contains neutral atoms. These neutral atoms are broken when the photons from the sunlight strike the depletion layer. This knocks the
Let's look at 5 main categories of advanced materials: perovskites, tandem cells, quantum dots, organic photovoltaics, and 2D materials. Perovskites are the rising star. They are cheap, tunable, and efficient in 2025. Lead-free tin perovskite cells achieved over 16% efficiency with long life stability. The main challenge remains durability and toxicity. This is the diagram of perovskite solar cells. Tandem cells stack materials with different band gaps. Perovskite silicon tandems now reach 31 to 32% efficiency, far higher than single junction silicon. Diagram of tandem solar cells. Quantum dots are nanocrystals whose band gap depends on size. They can capture more the solar spectrum with lab efficiencies above 18%. Diagram of quantum dot solar cells. Organic and polymer solar cells are flexible, lightweight, and even transparent. They are ideal for windows, wearables, and building integrations. Two-dimensional semiconductors like molybdenum disulfide offer ultra-thin, high-absorption layers. They are still experimental, but could enable futuristic flexible solar sheets. Recent highlights are Oxford PV started commercial tandem modules, Anchor launched a solar umbrella, and quantum dots are being tested in panels to boost their efficiency. Real world applications are these new materials power flexible gadgets, building integrated windows, and even high performance satellites. Key challenges remain stability under heat and moisture, large scale manufacturing, toxicity concerns like lead, and balancing costs. By 2030, we may see perovskite silicon tandems in mainstream use, organic solar in smart buildings, and quantum dots in consumer products. Here I conclude, advanced materials are reshaping solar cells, offering higher efficiency and new applications. With ongoing research, they'll play a major role in sustainable energy.